Okay. So today we're looking at the existence and uniqueness of solutions. This is a theorem that it's kind of going to underpin a lot of the work that we do. And it does have a lot of ties to direct applications, even though it can seem very theoretical. Okay. So be prepared. Today's going to feel a little mathy, um, but I will try to illustrate the point with some direct applications too for those of us who are more physically minded. Okay. Um, but the goal of existence and uniqueness of solutions is exactly that. We want to guarantee, hey, if we're talking about solutions, so modeling a situation, understanding a phenomenon, we want to know that such a solution exists, so we're not chasing after nothing, and that a solution is unique, so that there's not multiple ways to solve this problem or get from A to B. If there's many different solutions, then this is going to probably trivialize the problem or make it less interesting, or even maybe blow up our model and say this isn't a good model if there's multiple ways to solve this. Okay. So here's the idea. How do we know a solution exists and is unique? If we look back to a very basic function and we come at it from like a Calc 1 understanding. All right, we're not going to get too deep into the weeds here. Consider the function f of x equals 2x minus cos x. Can we find a solution for f of x equals 0? So you might march along here as I would. I mean, say, all right, I want to see if this thing can equal 0. So I set it equal to 0. I go ahead and solve because I'm a good math student. Add cos x to both sides. I go to solve for x. Well, I guess I could divide by 2, and then I get this, but I need to get this x out of cosine, so I take arc cosine of both sides. And then I get, okay, arc cosine of x equals, maybe 2 equals x, and now I'm like, okay, what the heck do I do here, right? I can't solve this algebraically. There's no way to get a closed form solution. And, that is such a simple equation to just write down, and then to not be able to solve it with algebra should seem pretty disappointing. I mean, to a student at your level, that should seem pretty frustrating, but there's no way to solve it algebraically, okay? But intuitively, what do we know? We've got 2x is a line, cos x is just a simple periodic function. This should have a solution, right? This thing doesn't blow up anywhere. What's going on here? So some insights that we can have from Calc 1, because we can't solve it by hand. What we can say is we know that this function is continuous, right? F of x is continuous because it's the sum of two continuous functions, 2x and negative cos x. What does continuous mean? Well, it means that you never pick up your pencil to draw it, right? That's the informal definition. But it also means that at every point in the interval of continuity, that the function's defined at that point and the limit exists at that point. So it exists at each point and it looks like it's going where it actually goes. Okay, that's the idea of continuity. The limit exists at each point and it goes there. So then what we can say about that is, well, then let's look at, f of 0, which would be 2 times 0 minus cos of 0. Well, that's what? 2 times 0 is 0. Cos of 0 is 1, so this is really negative 1. F of 1, maybe another point of interest is 2 times 1 minus cos of 1. Well, cos of 1 is like 0.54 or something like this. We know it's greater than 0. It's not bigger than 2. We know that. And it's not negative. So we know it's greater than 0. So what does this tell us? at f of 0, f of x is down here. At f of 1, it's like up here. So somewhere in here, it has to cross the x-axis. Right? If it's continuous, that has to be the case. You can't pick up your pencil. You can't have the limit not exist there, right? It has to fulfill all these things. The other insight is, okay, we know that it has to cross there, but the question is, maybe it does it a bunch of times, right? It could, since it's got a cosine, it could be oscillating and going back and forth, right? Something like that. So how do we know it's the only solution? Another good question. But we can use this fact that f prime of x, which is what, 2 plus sine x? This is greater than 0 for all x. For all x in the reals, because what does sine do? Sine bounces between 1 and -1. So this thing's always going to be positive. That means that it's always increasing. If a function's always increasing, that means it can't bounce back and forth, right? That can't happen. It has to just go through that place once, so that we have the knowledge that this must be unique. Okay. It's continuous. The intermediate value theorem tells us it crosses for sure. It's always increasing, so this solution must be unique. There's only one of them that we're after. Okay. So this is kind of a similar motivation to what we're after with existence and uniqueness of solutions in ODEs. However, this is a static equation, right? This is a static equation because we're after just one single value. In ODEs, our solutions are functions. And we haven't really talked about what comprises a solution in detail. We're going to talk about that today. But it's the same idea. We want to know, all right, does a solution exist, and is it the only one that fits the description? Okay. So here we can do this with Calc 1. We're going to use some similar logic. So here's a definition of what is a solution to a differential equation. Well, if f of t and u is a function of two variables defined on a rectangle R meaning, right, you've got a tu axis, and I've got some box here that goes from A to B on the t-axis, and from C to D, let's do this, from C to D on the u-axis. Here's my rectangle R. I've got some region. And we say that a function is a solution if u of t, so a function is defined for all values between a and b, and satisfies that it stays between c and d for each such t. So it does something like this. Okay. You can draw infinitely many versions of what this u of t will look like, but it has to be defined for all these t values, and then it has to stay between these two bounds for each such t. So it stays in R. So it's a solution if that's the case. It's defined and it's differentiable, which means that it's continuous. I'm going to box this in because it's very, very important. It's differentiable, which means it's continuous. And so that u prime equals f of tu at each t. So it's continuous in this box. So it has to do both of these things. All right. And you guys will have these slides, so you don't have to copy down the whole definition if you don't want to. So let's take a look at an example. So let's say we've got the initial value problem here, u prime equals u squared with u of 0 equals 1. And so what we want to do is show that something is a solution. So if we solve this by separation of variables, right, u prime over u squared equals 1, and you've probably solved this exact one before, right, you'll get that up of t is equal to 1 over 1 minus t. This is the particular solution. So what does it mean to be a solution? Well, it's defined on a region R, right? And that it's continuous. Do we have any problems with continuity with this function?
T equals 1.
Yeah, t equals 1, we've got a problem, right? So you might be inclined to say, because we've kind of been trained well from our Calc 1 days, and thanks for that, by the way, we've been trained well to say, well, as long as you don't let t equals 1, like, you're good to go, right? It's continuous everywhere else. Here's the problem. The way that this is written, it says that it has to be defined in this box and it has to be continuous. It has to stay within these bounds of the box and be continuous. So when we look at the graph of 1 over 1 minus t, we see that we have this vertical asymptote here. This breaks its fulfillment of the definition if I were to include everything in its domain. So what you really have is only one of these two parts of this could be a solution. Okay? So it's going to be determined by the IVP. Our IVP was what? We needed the initial conditions at u of 0 equals 1. There can't be two curves that have this be the case. So u of 0 equal to 1, that happens here. And so there's no way, here's a better way to put this. There's no way in which you could draw a rectangle around this point and get it to include this leg over here, right? Does everybody see what I'm saying? I can't say, hey, yeah, this thing's defined, it's in the rectangle, it's continuous. The second I get over here, you're like, no, it's not. That's not continuous anymore, right? So what happens is that we actually have broken this solution. And so we say here that the solution blows up. And so this solution is really only defined for t values from negative infinity up to t equals 1. And we call this the interval of, I mean, there's a million definitions of that, or names of it. Interval of existence. Or validity is also, let's say validity is better. And so a way to think about this in physical terms too, because you're like, all right, don't let t equals 1, Mally. Like, we got it. Why do we, why we got to split hairs here? Where a solution blows up in the real world would be like where a solution meets its limit, right? So you can have a pretty good model for air particles in a jet stream being shot in a certain direction, right? But once it hits the wall, then it becomes completely chaotic motion. There's nothing that you can do to model the situation after that. It's completely stochastic or random, right? There's no order to that. And so this would be a similar situation where it's like the fan was blowing the wind particles and they hit the wall and then they scattered. That's the end of the solution. It's not like we pick up and then keep going after that moment, okay? So it's really the limitations of your model. Does that make sense? So we need to be mindful of the interval of validity. Okay. So here we would only be choosing this as our solution. We would not be choosing this. We would not be including that in our solution. Okay. Sometimes we can ignore this, but we rarely should. We should usually have this be indicated, especially when we have an initial value problem. Okay? So what is an interval of existence or validity? It's what we call the maximum domain. It's the largest interval that the solution can be extended to. Things like a vertical asymptote, this usually is what will end a solution, an interval of validity. Okay? It means the solution blows up. However, it doesn't have to be the case. With a ODE here, which I don't think I have the formula for, I forgot to write that down. But we were able to plot a few solutions based on this direction field, and the behavior that emerged based on the different initial conditions was as such. If we, came in kind of the middle of this stream here, we might diverge from this fixed point and come to this other fixed point, right? Dropping off here, kind of like a logistic growth. Same here, this starting down at u of 0 equals -3/2, we might just be increasing up to this equilibrium, but starting at a higher point, it might break away. Okay, so depending on what your initial condition is, could change the interval of validity, right? Because here, for this guy, this leg here, this has an asymptote here. I forget exactly where it is. I think it's at 0.7. This has a vertical asymptote here. So this is only defined for t values. This guy here is only defined for t values to 0.7 and beyond. Whereas this solution curve here, with this initial condition, actually spans all t values. Okay, so it doesn't just, what I'm saying is that it doesn't have to have an asymptote to blow up the interval. It can be very much defined by the initial conditions and the general solution. Okay, so what's an interval of validity? It's where your solution is defined. And so you have to be aware of the domain and your initial conditions. All right. So working toward the idea of showing that a solution exists and would be unique. So let's take a look at, because we've looked at so far examples where we've been able to solve them by hand and say, here's a solution, right? We've got it. Most ODEs are not solvable by hand, as we learned last time, right? Looking at a graph is worth 1,000 words. So here's another idea of why this is important. This equation is, again, easy to write down, not easy to solve. It's not separable. It's not linear. So does a solution exist? It doesn't seem crazy when we look at the direction field. It seems pretty reasonable, kind of predictable. It was able to graph a solution curve for me without anything going crazy, right? There's nothing in here that causes the derivative to become undefined. So it seems like it should, but how do we know, right? What are the criterion to kind of guarantee such a thing so that when we decide, hey, I want to see how this river flows, or hey, I want to see how this material does under certain stressors, that it's worth going after, that there is a solution, and that the solution that we would find would be unique, right? That when you press on your brakes in the car, it only does one thing. It doesn't do 4 things, right? It does one thing. So it seems reasonable. So here is the statement of this theorem. I'm not going to have you guys prove it. It is well beyond the scope of this course to prove such a thing, but we do need to understand what it means. Okay, so I'll read through it. So if we have a continuous function on the right-hand side, f of tu, defined on a rectangle in the tu plane, again, similar to what we had before, that rectangle in the tu plane, defined by these inequalities like we did before. And we also assume, so this function's continuous on the right, also assume that the partial derivative with respect to u is continuous at each point in R. And I have a little asterisk here to make sure that I explain to you why that's the case. But for right now, just go along with me, okay? You can take these to just mean this is a nice function on the right-hand side. Okay, it's got to be nice. Then for at any point t naught u naught, the differential equation has a unique solution with this initial condition on some interval. What this really means is just, with some window around t, which we can define with some real numbers, right? Around t naught. Okay, so t naught plus a little bit, t naught minus a little bit, that we have a unique solution in some window around there. So, two things to again go back and say. You need what's happening on the right-hand side to be continuous, and you need the partial derivative with respect to u to be continuous. Okay, I think I put in a note here. Oh, we're going to look at that in a little bit. That's what my asterisk was for. We'll come back to why we need this piece in a couple slides. I wanted to do an example. This is actually number 1 from your homework, so you're welcome. Use the existence and uniqueness theorem to show that this IVP has a unique solution for some t interval. So I'm going to show you how to apply this. We're not going to do this a ton. It's just important for you to have to kind of underpin your understanding all semester. Most all of the solutions that we work with, all the equations, that we work with this semester are going to fulfill this, all right? So you don't need to worry about it too much. But again, it's important to know. It's like, limits in calculus. You see them, they do come up. They're very, very important as a concept, but it's not like we're doing limits all the time. So anyway, use the existence and uniqueness theorem to show that this has a unique solution for some t interval around t naught. All right, and we'll be looking at this guy here. All right, so u prime equals u plus 3. Does this fit the description of the theorem? Well, we check two things. We check that f of t and u, right, because this is really of the form u prime equals f of t and u. Is this continuous? I should see heads nodding yes. This is continuous. This is just u plus 3. Yes. No problems with u plus 3. Thank you. Yes. So hence it is, therefore, a solution exists. All right. This proves that a solution does in fact exist. And B asks that the partial derivative with respect to u is continuous. Is this the case? Again, to kind of refresh you on this, we don't need to go into it in too terrible detail. It's to take the derivative of the right-hand side as if u was the independent variable. All right, so what's df du, or partial f partial u, excuse me. Use this partial language for partial derivatives of u plus 3. This is really just 1. All right, so is that continuous? Is the function 1 continuous? Heads are nodding, yes. Yeah, so this is good. Maybe I shouldn't be using red. That's kind of a confusing color to say yes. Yes, it's continuous because of this guy here. So what this tells us is that u prime equals u plus 3 does have a solution, and it's unique. Around t equals t naught. Okay, by this theorem. If one of those things wasn't the case, we would not have this fulfilled. And so we couldn't say that. And so again, that's an idea, that's a problem where it's, should we go in and adjust our ODE? Do we need to change the model itself, right? Or, do we need to change our assumptions, fix some parameters? What must happen here? So there are some implications from this. Are there questions so far, by the way? Again, I know we're kind of in mathy world a little bit here. Yeah. You have not done Calc 3 before this class. Right. No, no, you have not. So partial differentiation, all you need to really understand about this, sometimes this is covered in Calc 2, but it is rare, I'll give you that. Partial differentiation is to really just treat one of the variables as the independent, and it will be given to you here. Okay. So, to take so if I have a function of x and y, like x squared plus y squared, df, partial f, partial x, I gotta watch my language here. Partial f, partial x is treating x like the variable and y like a constant. So this would be 2x. Partial f, partial y would be what? Yeah. 2y. Because now we treat x as a constant and y as the variable. So it's really just kind of snapshotting the function with respect to one variable, treating the other as constant. It's like saying, I only want to turn one dial. How does this thing change? And that's enough for us to work with in this course. It doesn't come up too much beyond that, because this is an ordinary differential equations class and not partial differential equations, which again, I think I've told you is just next to impossible. Those things. They're awesome. They're fun, but it's like the Wild West of mathematics, of applied math. So thank you for that. That's a worthwhile. I think I saw some heads nodding there that was helpful. So some implications from this theorem. This theorem applies that solution curves cannot touch or cross. Okay. Why is that the case? Well, part of it lies in the fact of that partial derivative condition. The fact that the derivative with respect to y is continuous, and the fact that we are proving uniqueness means that at each point, right, I can't have two solutions crossing through this point. Right? That would mean that there's not a unique solution passing through this point. Okay, and so they can't touch, they can't cross, and this is going to be very important, especially when we get to graphical solutions or numerical solutions, that we build this into that approach, that we have this knowledge. So this can help you differentiate too between a problem that's solvable and not. But these things can't happen. So maybe if you zoomed in here and you'd see, well, they're close, but they're not touching. That's okay. But if they are actually tangent to each other, that's a breakdown of existence and uniqueness. Now I'll show you algebraically why that can't be the case with this example here. Why do we need partial f, partial y to be continuous? So this is an example that breaks it, and it should highlight why, without getting into the deeper math of things being what they're called Lipschitz continuous and all these things that are like, 500 level math. This should do the trick. So why do we need partial f, partial y to be continuous? Well, if you look, let's say we're interested in this problem. This is completely contrived, right? But the point is to just show you why. So y prime equals radical y. So, we can write it like this. It's a function of x and y on the right. You're not seeing an x. It's an autonomous equation, right? But we see that, this piece is continuous. On the right-hand side. There's no problems as long as, we don't go into the negatives, right? And we don't, because we're taking on these values, right? Or y of 0 is 0. So we're not dipping into that problem quite yet. However, the partial with respect to y is what? 1 over 2 square root of y, right? If you take the derivative of y to the 1/2, it comes back in the denominator. And now, what do you see? Y cannot equal 0, right? If y can't equal 0, that's a huge problem, because we're interested in the solution where this is the initial condition. And so what happens is that there are solutions. There are solutions, or solutions exist. They're not unique. So for example, y equals 0 fits, just the y equals 0 function. So does the function y equals 3/2 x squared, right? That's equal to 0 at y equals 0. And is this equal to its own square root? Well, maybe not, but something equally easily contrived could cross through there. There's multiple solutions that exist. Could satisfy y prime equals f xy and y of 0 equals 0. So this is the type of thing that we want to avoid, because a lot of times finding the solution to an ODE is expensive. And I mean expensive in terms of computation power, manpower, coming up with a viable model, right? Do we need to spend our time on the solution or not? So this guarantees uniqueness. So that's why we need to be able to show that it's continuous. If you dodge the domain issue because you're on a curve where that's not a problem, then it's okay. But remember, you need to be on a solution curve needs to be continuous. It can't have any breaks in it, as our definition. All right, I don't want to do that one yet. All right, let's do example 3 before example 2. Are there any questions so far? Okay. So let's do example 3 here. And then we're actually going to take a break, and I'll set you loose on some problems before we do example 2. So here's another example to talk about the concept of the maximum domain. Again, this has to deal with the interval of validity and how you'd find this. So u prime equals 2 minus u. And really, I'm kind of just training you today to be hypervigilant about domains of things, okay? So u prime equals 2 minus u with u of 0 equals 2. So I need this. I need the curve where this is my initial condition. And this is something that we haven't talked about quite enough, so this is going to be good. So you go ahead and solve this, right? This is separable. Here's where we need to discuss our interval. And that is that at this point, right, we have made an assumption by separating these two variables, right? What assumption have we made at this point? Are we going to let u be 2? No, we can't let our u value be 2. So when we do this, we're saying, all right, at this point now, we cannot have u be equal to 2. So then this breaks down this trajectory of trying to find this method of trying to find a solution. When we do this method and we separate variables and we have a restriction like this, this is implied as we carry it forward. Since I need this in my initial condition, then what is the only solution that would work? There's only one that doesn't break this down and that solves this. You can do it. Don't think too hard. It's just the constant function 2. All right, u of t equals 2. Does this fit the bill? Yes. Right? What's u prime? If this is my up, what's up prime? That's 0. Left-hand side would be 0. Right-hand side would be 2 minus 2. That's 0. That checks out. This is what we call the trivial solution. And it's always available, and it's rarely what we care about, right? But we have to name it that there is a solution that fulfills this, but we can't find it through this method of integrating factors or separable equations because of this implied restriction. So this was a little roundabout way of talking about this. What's the real thrust of this question? It says find the maximum domain of the solution. Well, the solution we care about here is the trivial solution. Do we have any domain problems in the trivial solution? Can I plug whatever I want into u of t equals 2? I should be seeing some heads nodding. There's no problems with a constant function, right? It always puts out the same thing. I give you t equals negative a billion, you're giving me 2. I give you t equals 4, you're giving me 2, right? So there's no domain issues there. So here the maximum domain is negative infinity to infinity. Okay, but this is another thing to consider here unto itself, that when you go about solving in ODE, you need to be aware of the restrictions you're placing on the solution by your method. And if you break your initial condition, then probably the only way you can go is using the trivial solution. All right, so it's kind of a twofer example. Questions thus far? All right, we're going to pause. I'm going to have you guys do some practice. All right, so we're coming back and we're going to look at this physical example. And we're going to look at the Newton's law of cooling. And this is in a general form, meaning where instead of just that K sitting out in front, the law of cooling is really the output of this function h of u of t minus a. Okay, so where the temperature of the object is that unknown function u of t, and where h of x, h of whatever, is a continuously differentiable function for all x, and a is the ambient temperature outside, okay, or in the environment. The typical law of cooling that we use was what we've seen before, that h of x is really just negative k, some constant of proportionality times the difference between the object and the ambient temperature, right? So how fast something cools is proportional to the difference between their temperatures, right? And the closer they get together, the slower that rate of change becomes, and it slows to 0, right? The beer will warm to the outdoor temperature, the coffee will cool to the room temperature, whatever. So we're going to look through these parts to kind of highlight the physical nature of the existence and uniqueness theorem, or the physical perspective. So let's use this theorem to show that this does have a unique solution for any initial condition. So for part A, let's remember that, all right, u prime is a function of t and u on the right-hand side. It's really h of u of t minus a. So it's actually an autonomous function because there's no function of t over here, right? A is constant. Are we assuming A is constant? Yes. So it's autonomous. And what did we say with our assumption that h of x is continuously differentiable? Okay. So for that first part of our existence and uniqueness theorems, we can say that, yeah, h of u minus a is continuously differentiable, which is a stronger condition than just being continuous. If it's differentiable, then it's continuous. Okay? Right? So it is continuous. So this is great. So we know that a solution will exist. We know the right-hand side is nice. It's not some crazy function h that some evil math teacher would come up with. It's going to be a nice function. Okay? It's going to be smooth and differentiable. So now that second part of uniqueness, having the partial derivative with respect to u, is this continuous? Well, we'd take a look at the right-hand side, and what would we come up with? We'd come up with, h prime of u minus a. If something is continuously differentiable, that means that its derivative is also going to be continuous. Right, so that's also here. So it does, in fact, fit the bill. Both of those things are continuous. Hey, this thing's going to have a solution, and it's going to be one of a kind passing through that particular point. All right, now to kind of speak more to the physicality of it. So part B is asking, why would the condition h of 0 equals 0 make sense? So, we have an initial condition of h of 0 equals 0. Why would this make sense? Does anybody have an idea?
If it's continuous at all points, this should still be continuous, right?
Right, it will be continuous there for sure. Right, we know it's continuous at all points, so this is great. And we know that if we have it be passing through there, it will be continuous. The question is, why does it make sense, like more in a physical context? Like, why does h of 0 equal 0? Why would this make sense in terms of a cup of coffee cooling down? So you have to look at this here. Right hand side being h of u minus a. If this equals 0, if h of 0 equals 0, that tells us that h of some u minus a, some u particular minus a equals 0. And that would mean that this needs to equal a. Right? It would need to, and the input, be equal to the ambient temperature minus the ambient temperature. Right? We would need up of t to equal the ambient temperature. So why would this make sense? So if we start at the ambient temperature, right, then the amount of distance between the object, right, if you just start with a cup of tea at room temperature, a cup of water at room temperature, it's going to stay at room temperature. It's not going to suddenly warm up. It's not going to suddenly cool down. It's going to stay at the ambient temperature, right? And so it's going to pass through here, and we know that u prime will be equal to 0. And that should make a lot of sense too, because again, it's not going to be changing temperature if it's staying at the ambient temperature, right? It's going to follow the temperature of the room or the outdoors, whatever that might be. Okay. Does that make sense? So h of 0 has to equal 0 here. Okay. And then lastly, maybe we'll just discuss this because I'm out of room too. But why would it be reasonable to impose the condition that h must be a decreasing function? H has to be decreasing.
Well, given the context, the, it's a law of cooling, so that's losing energy, so it's a constant decreasing event of some kind. There's no
Right,
energy being put in the system, so there's no addition or growth of some kind.
right, right. You assume that these starting temperatures are going to be higher than the ambient temperature, right? And that there's no magical temperature in which, right, once you're past, let's say, 20 degrees higher, that's not just going to start taking off and rising on its own, right? It's the higher the temperature starting, the faster it's actually going to cool down, right? But they're all going to tend towards A. And so, yeah, that rate of change needs to be negative for all such cases. And so then the derivatives are going to be related in that way where, you know, if this is the case where, U1 starts higher than U2, right? So it starts higher on the temperature scale up here. Here's U1, here's U2. This thing's going to drop faster to the ambient temperature than this thing will, right? So their derivatives will be related such that, U1 prime is going to be more steeply negative than U2 prime. Does that make sense? So something that starts off hotter has got more to lose faster to get to the ambient temperature, right? Okay. So again, a little bit about why, having a unique solution matters. Um, you know, why having more than one wouldn't really make sense in this physical context, right? Um, so hope you find that illustrative. And I'll end the video here for today.